So I actually have one or two pictures. I was planning on having no pictures, but suppose you want to represent something like this. The way we usually think about doing it is breaking it into pieces, right? Pieces with shared boundary. You don't have to do things that way. You could break it into pieces like this, where I'm sharing the cells and the edges instead of sharing the vertices and the edges. It's completely equivalent.
Try to do screen share. I don't think you're actually doing it yet.
Oh, doing what? Oh, screen share. You're right. Mute what? I muted my box. It's not muted? Oh, I thought I was supposed to not mute myself on Zoom. I'm supposed to mute myself on Zoom?
No, you can hear you on the screen. It's good.
Okay. What am I doing wrong?
It's good. We can hear him on the screen. You're good.
It
Okay.
actually sounds fine on my end, so you're not doing anything wrong.
Thanks, Todd. Actually, the other Todd. I am also Todd. So if you want to represent a mesh, you would like a way to do it that doesn't depend on the details of the mesh. It shouldn't depend what shape of cell you have. It shouldn't depend what dimension the cell is. It shouldn't depend if you have different shapes put together to make up the mesh. So how can you do that? And it turns out that there's a topological description that allows you to do that, and it is the process, you describe the process of putting things together. And so, for instance, if you do it really simply, if you look at this triangle, you can imagine that the triangle is a thing that is bounded by three edges. And so the topology of the triangle is a thing with three boundaries that are joined together. And in fact, those edges have boundaries as well, and topologists use this. They make a formal sum and they say, look, the vertices cancel out and the boundary operator acting on itself is 0, so it's nilpotent, right? You can continue this process. So then this triangle, 4 triangles would bound the outside of a tetrahedron, and how many tetrahedrons bound the outside of the next simplex up? But you can keep going up in dimension. And the thing is that you can represent this, it's a relation, right? It's a binary relation between K cells, usually between a K and a K minus 1 cell, but you could have relations between K cells too. And so you can represent this relation as a graph. So I could say that I have triangle 0, and then edges 4, 5, 6 are related to that because they bound it, and then vertices 1, 2, and 3, what? Oh, yeah. Vertices 1, 2, and 3 are related to those edges. And so I can do it for a more complicated one. You can have 2 cells, and then you have 5 edges, and then you have 4 vertices. And you can do this for any shape of cell, any dimension. And so there's an isomorphism between directed acyclic graphs and meshes. If you give me a DAG, I can draw you the mesh. If you give me a mesh, I can make the DAG. And in fact, I don't even need the intermediate levels. I can reconstruct them in linear time using lattice operations like meet and join. I can also use graph operations to replicate all of the things I need to know about meshes. So for instance, I would like myself and my boundary, or the closure, and the closure of this element is actually the transitive closure of the relation. And there's a dual operation, which we call support. If I had a dual basis vector centered at 5, the support of that function would be the support in the relation. So I can rewrite all of my discretization stuff using graph language. Why? Because then the same works for any dimension, any cell shape, any combination of cells put together. So I don't have to write special purpose code for every new thing that I want to do. I write it once. And then I write it 5 or 6 times for it, as it would be crazy if we could write once and run on all this different hardware. This is almost enough. except if you look at the way these things get stored, I might store the relation in memory as storing the ordered one level up for each one, which we'll call the cone. So I store those, and then I store the same thing for the edges. But say I want to make a query like, I'd like the closure of this triangle. So I get all of the boundary here. So 6, 7, 8, 4, 2, 2, 3, 3, 4. That's fine. But if I look at it for 1, I get 9, 10, 8, 3, 5, 5, 4, 3, 4, because that's what 8 is. And unfortunately, that's not really what I want, because I would like the boundary to be positively oriented. And so here it's oriented correctly, but here I need to flip around what I get out of 8 in order to orient it correctly. So I need an extra piece of information, and I can put that extra information on every arrow in the DAG. So every arrow in the DAG is decorated by a dihedral group for the face that's being attached. The dihedral group for edges has 2 members. It is 2, so I can use 0 and -1, but it's more complicated for other kinds of things like quadrilaterals, right, which have 24 or some orientations or something. So this is what a plex is. It is a graph. It looks like this. And so if you generate one, that's what you get. So here is the way I recommend you make plexes. You copy these 4 lines down, and that's all you should really need. And you can do everything you want to do from the command line, which is the way I like to do things, because I don't ever want to change the code or recompile or do anything like that. So for instance, you can give this option, and it will read in that file and make the plex. So if you create example 1, you can run this and load in, for instance, a Gmesh file. We support, I think, everything in Gmesh now. Yeah, no, high order works now. What? Oh, high order simplices, that's right. High order quadrilaterals work because we know what ordering is, but I need to write the lexicographic ordering for high order simplices. So that's broken. Although what you can do is you can read it in as low order and then project to high order, but you, but you would lose. Oh, really? Mm. But when you output, yeah, we support 2, 3, and 4, and 4.1 of Gmesh. Yeah, and so when you read it in, I usually output something like this. It says, oh, there's 30 vertices or 0 cells and 42 triangles or 2 cells. And this gives information about things that are labeled, like how many of what cell type. That's a triangle, that's a vertex. Then depths are just, since this relation is a partially ordered set, it's actually a graded post set, so you can talk about depth from the root. And so depth 0 is vertices, depth 1 is. You can also have it on the fly do things like create the edges and faces, and therefore you'd have the edges this time. And so I'm really outputting a little description of the graph, and then you can get it to output the whole graph. Here, let's just do it. So, what am I running? Example 1, and, well, certainly I can make this thing output it too. So, if I say DM view, so it outputs this tiny little thing, and then I could say, okay, I want it to refine that thing twice, and I can make it bigger, and then you can say, okay, I would like it to output the whole graph as an ASCII thing, and so those are the labels. So what it says is, okay, these are quads. So this quadrilateral has as its boundary edges 65, 41, 43, 73. So if you go down here and look at like 41, edge 41 is 33, 16, so 44 is 16, 37, 16. So one of them's got to be negatively oriented for them to match up, and it is, right, -1. So you can walk around and figure out the whole mesh from this, and obviously this is the most intuitive way to look at meshes. So this is what I usually do. But you can get it to tell you it in different ways. So to make the pictures for these talks, I did things like this. And so it'll output, you know, a TIX version of this mesh, which I then cut and paste into my LaTeX. And you can customize it by, you know, which things get output. Does it draw the circles for everything or not? And you can make these kind of, you know, things that I made here, right? And you can make this like the Mobius strip and stuff, right? And there's other things, kinds of transformations. Let me see, what did I want to say about that? So there's a bunch of different things you can do with that, like you can tell it you want it distributed, you want to use a certain kind of partitioner. What am I doing here? You can output it to HDF5 and view it like this, and it'll generate different shapes for you, like a box or a ball or a sphere or a cylinder, and it'll read in all these different formats. The most interesting thing to me is now that we can read in CAD formats. So you can read in step files and IGES files and stuff. So if you have CAD that you would like to use and you want the refinement to stick to the CAD surface, it will do that. And you can also write them out. So you can, okay, so my student, Brandon Denton, did all this work, and the last thing that he did is not merged yet, but that's what we're heroically trying to do, or he is, this summer before he goes to his new job, and that is we have a method for exposing the B-spline that is underlying the CAD model. So we have a shape optimization running where what normally happens, so for instance, FireShape is a great package, but what it does is take a mesh and do shape optimization, move the mesh. That's not great because you cannot take a mesh and go back to CAD and then manufacture it. So what we have in the example that hopefully will merge shortly, but you can always look at it in the fork, is an optimization where we don't optimize coordinates for the mesh, we optimize the parameters in the B-spline representation directly. Then you can write out that optimized CAD and fabricate directly based on that. So that is more of the kind of closed loop system that I am after. I want us to go from analysis to fab back to analysis in industrial environments. Okay, I'm done.
Thanks, Matt.
Yeah. Yes.
Richard wants to needle him. 1 second.
Okay.
I